Hi, I'm Paul Macklin, and welcome back to the PhysiCell 2023 Virtual Workshop and Hackathon. This is session 1, where we're going to learn how to work with projects in PhysiCell. So the session goals here, first of all, as we noted, we're going to learn about how to work with sample projects in PhysiCell and how to work with user-driven projects in PhysiCell. And this will help you as we get on to learning and building your own specific projects. So first, I'd like to point out that every PhysiCell download comes equipped with a handful of sample projects to kind of give you a running start of seeing working projects that others have built in PhysiCell. Probably the most important project that we provide is the 2D, 3D template project. This should be basically always your starting step if you were building your own project. Start with a template project that has everything kind of ready to go. All the initialization is done, and you can really focus on doing your customization for your particular biology, which cell types are there, which diffusible substrates belong there, and things like this. So this is probably the most important sample project to go with, but we'll show you a few others we can go to see kind of some modeling ideas. And so to get at these sample projects, the first thing you want to do is type make project name, so whatever the sample project name is. And what that's going to do is there's always this two-step process here. The first step is to populate the sample project, is to take all the files for that project and put them where they belong into the PhysiCell working structure. That way you will be ready to build it. And then you type make to actually compile that. So there's two steps, right? First is to load the project and put the files where they belong. The second one is to actually compile it and get it ready to execute. And you run your project. And then when you're ready to go, there are a few other makefile rules that are going to be quite handy. One of them is make data cleanup. That is to clean up all the output data to get ready to do another simulation. Make reset is a way to return to a clean state. So that is to depopulate the project. So you're working with one of the sample projects. Now you're ready to do your own. We'll type make reset, put everything back the way you found it. Type make template to load in that template, and now you're ready to start your own project, for example. And if you want to see what list projects are available, you type make list projects, and it'll show you all the currently supported sample projects in your version of PhysiCell. And so let's take a look and actually get some practice now in building some of these sample projects. So I'm going to go here into a terminal window that's open in my PhysiCell directory. So here we are. And I'm going to type make list projects, and now I have a list of all the sample projects that are available to me, and I'm going to populate one of these sample projects in particular, make, and then the name of the sample project. Let's go with the biorobots sample. So this, you may notice, has copied a bunch of source files around in the PhysiCell structure, but hasn't actually compiled anything. So we need to do one more make to actually compile and build that project. So let's go in. Let's go ahead and go to the next slide here. So this is compiling. While we're at that, I would like to actually take a look and lead you through the typical structure. So let's continue compiling this, by the way. So the typical structure of PhysiCell. So this is what you should see when you download PhysiCell for yourself. You're going to see that a number of subdirectories. Some of them you're going to be working in, some of them you're going to be mostly ignoring, that they're actually part of the core structure of PhysiCell. The root directory, this overall directory, is where the main makefile and your executable and your source code will go. Some of the other directories that are increasingly so important is the add-ons directory. This is where things like PhysiBoss or LiveRoadrunner or other officially supported add-ons for the ecosystem are included with your PhysiCell download. Beta, don't need to worry about. BioFEM directories where the diffusion solver is stored. Config is one of the more important directories. This is where your configuration and model specification files go. Documentation is unfortunately deprecated. Excuse me, sorry. And so that's where we're going to be doing some work in the coming years, particularly with the community. Examples is an old version of sample projects, and so that will be removed in the future version. Licenses is where we keep licenses for some of the add-ons. MATLAB has old MATLAB scripts, although typically we prefer Python these days for post-processing and analysis. Modules include some other standard add-ons for PhysiCell that are now pretty much always used in PhysiCell. Output's important. This is where you're going to store simulation outputs when you're done running a simulation model. Pavre is deprecated, is where we used to put 3D visualization files. Sample projects is where we store a handful of sample projects with their source files kind of in subdirectories to have it properly structured. Sample projects intracellular is just another version of this for intracellular add-ons. Testing unit tests are just for our developer sanity checks. And now another important directory is user project. And so down the road, as you start building your own PhysiCell projects, you will be saving them in user projects, and then you can save and reload and pack them and share them with others as you need to. So when you tend to work in PhysiCell, most of your work will be in these red directories. In the root directory, the configuration files, custom modules, which is where you would put any custom C++ source files. Output is where your simulation saves, and user projects is where you save your overall project in case you want to switch between different projects. So now, if you were to open up the main configuration file, so let's, for example, go into config, and we can see that there's a file called PhysiCell settings. .xml. So let's go ahead and open that up. And you can see that this is really grouped into a handful of blocks of XML. Right now, I'm just going to shrink these down to make it easier to navigate. But you can see, in fact, we'll just go back to the slides here, that this is broken up into general sections. Domain is where you have set up for the simulation domain, helping in X, Y, and Z, and things like your discretization, if you're delta X, delta Y, delta Z. Overall is overall settings for how you run your simulation. Probably one of the more important things you would want to care about, if I show you, expand this out, is max time, saying how long do we want to simulate in time for the simulation. These are units for our own sanity checks, and then there's step sizes for diffusion, mechanics, and phenotype, which I think we talked about in session 0. Parallel gives you things for OpenMP parallelization, like how many threads do we use. Save is also something you might want to look at. You can change where you do your saves for your simulation. You can, here in this folder setting. So you can, for example, change this to output 1, and now this would save all your simulation data in output 1. One word of caution, this is a little bit of a philosophical statement, but you can only save places to places that exist. So if you specify that output 1 is where you're going to save, if there is no output 1 directory, then your data are being written to the ether and do not exist because output 1 does not exist. So if you change this folder, make sure you actually create it so that you have someplace to save. Okay, and then these are like how often do you save the full simulation data, in this case, every 2 minutes of simulated time, and how often do you save your quick visualizations as SVG files, in this case, every 2 minutes. Microenvironment is where we're setting up things like diffusible factors. In particular, everything has a name, units, diffusion coefficient, decay rate, and then Dirichlet conditions, which basically says how do we handle the boundaries of that diffusible substrate. And then as we go further into this config file, we have things like cell definitions. So every cell type in your simulation will have a big block of code in this markup language. And then lastly, at the very, very end of this file is a section called user parameters. And that's where specific parameters for your model that don't belong in individual cells, but maybe are more global to your simulation would be stored. And so we'll talk more about those in later sessions. I want to point out that there are other configurations files that you might see in this config directory. In particular, you may notice a cells.csv file. This is a comma separated file with basically the cell type, an X, Y, and Z position, and they can use this to list the initial positions of all the cells in your simulation. So we can parse that and seed the initial positions of the cells to a more interesting geometry or something you might read in from some other utility. Rules.csv is something brand new this year, and this is where we can do the actual rules that form the hypotheses of your models. For example, oxygen increases cycle entry, or doxorubicin increases apoptosis. These kinds of rules end up written to this CSV file and parsed at runtime to build your model rules. And so that's something you will often now see in the config directory. If you're running PhysiBoss, then you might see a number of BND files in the config directory. And this is where the Boolean network models are defined. And if you run other add-ons like Live SPML or Live Roadrunner, PhysiMess, or DFBA, you're going to see their own particular config files in that configuration directory. And so now it's good to kind of understand the overall structure of your C++ code in these models. If you go into custom modules, so I'm going to go here and go into custom modules. You will see basically two files here, custom.cpp and custom.h. As you may know, in C++, a header file, a .h file, is where functions are defined, and a .cpp file is where they are actually fully implemented, encoded, so you can execute them. So header files define functions, give you the syntax, CPP files implement them. And so if you are building custom functionality for your model, you will probably define those functions in your custom.h and then actually implement those functions in custom.cpp, and then we compile and link them all in. There are a number of functions that are already in custom.h and CPP based upon your template, things like setup functions to help us set up all the cell definitions and any other custom functions or custom coloring functions that are more advanced usage. So this will all be in your custom.cpp and h files in the custom modules directory. So this is one of the directories where if you're going to write your own code, your things will probably go here. That's where they would belong. Okay, other things to know about. If you go deeper into the structure of custom modules, one of the most important functions is called create cell types. And this is where you would do things like define the default phenotype for the different cell types and add any custom data and set the functions for the custom functions. Now, the interesting thing is, starting in 2023, where we have rules-based modeling, you probably won't need to actually do this. We can do this graphically now rather than in code. Likewise, setup tissue is a function in this custom.h and CPP file where you can actually do a lot of custom initialization for individual cells. So if you're just worried about placing cells in the environment, you probably don't need this. You can use the CSV files. But if you want to have fine-grained control over saying on a cell-by-cell basis, I want to choose an individual value for some parameter, this would be probably the place to initialize that for now. Okay, and then if you go up in the structure, so back into the main directory, you'll see something called main.cpp. And like many C++ projects, main.cpp is kind of like the main entry point for the program. And this is where the overall structure of our agent-based model goes. Remember, yes, in our last session, in session 0, we talked about the overall structure of an agent model. We said you do your initialization at the top, and then after that, you enter into your main loop and start doing things like updating the microenvironment and then updating all the cells and looping that until the end of your simulation time. Well, main.cpp provides that structure. And so at the beginning, you have a number of setup functions like set up the microenvironment. And typically, if you're going to modify this further, you might do this in custom. And then we're going to create all the cell types. And then we're going to set up the tissue to put in examples. So create cell types where we make all the cell definitions. And now that we have cell definitions defined, we can go ahead and set up the tissue by placing instances of those cells or individual cells in the environment. And so that's all right here in that setup function. There's also a place in main.cpp before you enter the main loop to actually add any custom coloring functions. So this might be something that some of you might want to do beyond the built-in coloring of PhysiCell. Lastly, you get into the main loop. We have a section where we first do saving the data, then we update the microenvironment, then we update all the cells, and then at the very end of the loop is where we update the time. So you can imagine, since our simulation loop goes update environment, freeze environment, update cells, update time. If you want to do something custom, like some kind of your own extension or add-on, that would be a good place to put it. Say, freeze cells, update environment, freeze environment, update cells, do something custom, like say, grow a vascular network, update time. That would be the right place to put it in the overall structure. So one last point on C++ source files. Most modelers now will be using the cell behavior grammar that we'll introduce in the next few sessions to write their models. And in that case, these kinds of models will not require you to model any of the source files you just saw. And so you probably won't be writing much C++ these days. However, it is wise to understand the overall structure of PhysiCell and where the different source files are. In particular, this gives you a notion of which files are yours or specific to your project, the things that you can change without worrying about compatibility, and the things that belong to PhysiCell's core library, the things that are going to be changed by us, and the things you should probably not mess with, or let us know that there are bugs so that we can fix it for everybody. And that's so you should be making your edits probably to your own project. But again, if you find that you can't accomplish what you need to do without editing core source files in PhysiCell, that's time to reach out to us, and we can make architectural changes to make your project more feasible and to share that advance with the whole community. Lastly, PhysiCell ecosystem developers may need more of this technical knowledge. And in fact, future workshops may actually split into one for general end users who are making models, and one for ecosystem developers. But this year, what you might want to do is look at the agenda and look for any sessions that are marked as advanced. And those are the ones going to dig a little bit deeper into the technical underpinnings of PhysiCell, which would be really good background information for you if you want to make contributions to the ecosystem. Okay, so now let's get back to working with the sample projects. So we already did this, right? We said we want to work with the biorobot sample project. We typed make biorobot sample, which put all the source files where they belong, and we typed make again to compile it, and now we're ready to execute the project. And so if you are on Windows, you would type biorobots.exe like I've done over here, and that's the name of the executable. If you're on Linux or Mac OS, then you do /biorobots and hit enter, and that will start executing that particular model. And so if I were to let this model go for a while, it would take maybe just a few minutes to run. We can see how we're running through, right? And you see some output to the screen showing us that this thing is making progress. Here's the current simulation time, the number of agents in the simulation at the time, and how long we've been running this executable so far. So far, in the time we've been talking, we've gone about 20, 25 seconds. And, I'm impatient. I'm just going to hit Control-C to cancel it. But we got some data out of our simulation. Now let's take a look at the data that we've saved. And so if you go into the output directory, you're going to see a whole lot of files here. In particular, you'll see a lot of XML files. These are kind of like basically multi-cell DS information that gives overall structure of our saved data, like what simulation time it is, where to find your source files, things like this. Then you're going to see a lot of map files. And these are basically binary compressed MATLAB files that have a compressed form of the cell simulation data and the saved substrates. Say, if you were simulating oxygen would be saved here. And then the other things you'll see is you'll see a lot of SVG files. So let's just open one of these. So Mac, you can just type open in a file name, and I'll use its default viewer, say 139. And this is an SVG file, a scalable vector graphic that was created on the fly to help visualize our simulation at this particular time. And so these are actually really nice because you can easily incorporate these into other graphics and their publication quality because they're vector graphics, not rasterized, which means that if you rescale them, they don't lose quality. So we have those. Now, there are a few more things here actually that I didn't actually put into the slide deck. Oh, okay. You know what? We'll get back to these actually. So these are fun. So one nice thing to know about now is we have all these SVG files. You may want to do things like create JPEGs, which are a little bit smaller than SVGs. And so if you have ImageMagick installed, you can use Mogrify to script these. You can do Magic, Mogrify, reformat them to JPEG, maybe resize them down by 30%, and work on all the snapshot files or some of them, and it will downsize them. And then you might want to convert those JPEGs into an animated GIF. So that can be quite handy. So here's an example of doing that. But actually, in most of our projects now, we create makefile rules that are actually designed to make this much easier. So if you are in, for example, your root directory, you can type make JPEG, and it'll convert all of the JPEGs, all the SVG files, all these snapshot files in your output directory. It'll convert them into JPEGs that are ready for animation. You can also type make GIF to take all the SVG files and automatically convert them into an animated GIF file, which is nice for things like social media. A little bit harder control, but it's quite nice. The other thing that I think you may find quite handy is make movie. And if you type that, it will create an MP4 file with a nice, balance of compression versus quality that is compatible with things like PowerPoint. And so that can be quite handy too. So here I'm running make JPEG, and if you were to look, you'll probably see it creating a whole bunch of JPEG files. I'm going to hit Control-C and cancel this. But see, in the output directory, now we have a whole bunch of JPEG files. So now I can type make movie. I'm just going to take all of those JPEG files that are available in that directory and stitch them together into an MP4 file called, I think, out.mp4. So let's go into output. And we have all these MP4 files. I'm just going to open out, no, probably with a typo, open out.mp4. And now I can just play this MP4 file that was generated by PhysiCell. And so you can use these kinds of commands, or either with built-in makefile rules or more manually to get finer grained control to manipulate the quick visualizations that are made by PhysiCell. Okay, so we've made that now. Now we may want to switch to another project. So let's get a little practice on that. So before we do that, it's probably good to tidy up our mess. So let's get back to our root directory, and we type make data cleanup. And it'll remove all the data that was created in the output directory. So you can see now that we have a much cleaner directory and we're ready to run another simulation. And now let's say we want to switch projects. Well, before we do that, we have to depopulate this project. We have to get back to a blank slate. This is a common mistake to forget to do this. So type make reset. And now everything's kind of back the way we found it when we downloaded PhysiCell. And then we type make list projects again and see all these projects that are available to us. And so let's get some practice now. I want to provide a little bit of insight and background in extensible markup language, which you may need if you're going to go and manually change some of these settings without using a graphical editor. So XML stands for extensible markup language. You can kind of think of it as a generalization of a hypertext markup language, or HTML, which might be more familiar to you. Information in XML are stored in elements. And those elements are the name of your tag, any attributes that may be attached to it, and then the actual value of that element, and then a closing text that matches the opening tag. And so that's basically what we have in typical XML files. And sometimes you can nest these to get more complex forms. But really what you want to look for is the name of the thing you want to change, some attributes which may be optional, and then the actual value of the thing you want to change, and type it over here. So that's what we want to be looking for. So you can have sub-elements too, like let's say, some parent element and the sub-element. And so these are some of the conventions here. Typically, we would have the name of the tag as the name of our parameter that you want to change. The attributes might include things like units, say microns per minute squared. In PhysiCell, by the way, spatial units are defaulting to microns in PhysiCell. And we assume microns everywhere because we don't do unit conversions. So make sure that you do some sanity checks, right? If you are looking up a parameter value for, say, a diffusion coefficient from the literature, it's probably going to be reported in centimeters squared per second. But the default length unit in PhysiCell is microns. The default time unit in PhysiCell is minutes. So you need to make sure you convert that to minutes squared per micron to be mutually compatible with everything else in the simulator. So just kind of remember to think of in terms of microns, because that's kind of the characteristic size of cells, and minutes, because that's kind of the characteristic timescale of cell movement and activity. Okay, so we're going to take this knowledge now, and we're going to go ahead and switch to a different project. So we already did our make reset. And now we're going to do make list projects to see what's available. And we're going to change to the cancer heterogeneity project. So make, let's see, it is right over here. So we type make heterogeneity sample. That populates the project. It moves all the source files where they belong. Type make again to actually compile that. And then we're going to change a few of the settings manually for now. And so we're going to go into the configuration file here. So I'm going to close these because I've changed a little bit. So the easiest way to do that, at least on the Mac or Linux, is to go into my config file directory. I'm going to open PhysiCell settings, .xml, and I'm going to keep this this text editor open here and start changing some of the properties of the simulation. So we're going to do just a sample. We're going to simulate a shorter simulation of 2160 minutes, or a few hours. We're going to do a smaller domain to speed it up. we're going to set some of the parameter values here. We're on something called an oncoprotein in this particular simulation. So let's, and then we're going to go ahead and start and run this thing. So first, let's go ahead and change the domain size. So we go into this configuration file, and we go here into the domain section. I want to go from -500 to 500. So 1 millimeter total of microns here, right, in X and Y. So I just go ahead and change this value here. And now I've changed my simulation to be 1,000 microns in X, 1,000 microns in Y, and I'm going to leave the Z alone because I'm going to go, remember, PhysiCell actually doesn't simulate 2D. It simulates a very, very thin slice of 3D, 1 voxel thick, going from -half delta C down to +half delta C top for a total of 1 delta Z thickness. And so that's how we simulate 2D. And so if you want to do a 2D model, usually just leave these Z domain ranges alone. And of course, if you do this in the graphical editor, which you'll see in the next session, this gets a lot easier. Okay, so we changed the domain size. Now we're going to change some of the user parameters. Oh, you know what? We've got to do one thing. Oh, okay, yeah. We'll go and change this oncoprotein value first. I want to change the mean to be 3. I'm sorry, actually, I want to change the mean to be 1 and the standard deviation to be 3. So let's go here and find the user parameters section. Here we go. And the oncoprotein value has a mean of 1. I'm going to change the standard deviation from 0.25 to 3 to have a lot more heterogeneity in this example. And I want to change the maximum value of this parameter to be 10. So these are just parameters that are very particular to this specific model, and that's why they're here in the user parameters section. Okay, so we've changed those settings now. And remember, I want to change the simulation time to be much shorter. So I'm going to go back up to the overall block. And I'm going to change the maximum simulation time down from this amount of time, which is like 2 weeks, I think, down to 2160 minutes. And I also want to slow down how much data I'm saving and simulate the full data only every 6 hours, so every 360 minutes. And everything else we're going to run, leave. So I've already compiled my project. So if I'm in my root directory, I can go ahead and run it. The executable name is actually told to us by the compiling that the executable name is heterogeneity. So /heterogeneity, and go ahead and run this model. And it shouldn't take too long to run here. So it ran, it read our parameter values. It told us that our actual standard deviation was a little lower than we specified, probably because we cropped our distribution here. And we're simulating this thing out for a few times here. So we've already done, looks like 12 hours of simulation so far. So we're getting some pretty good progress. We're about 1/3 done. And so we'll go ahead and let that run. And what I'd like to do is let this round up just a moment longer. I might just cut this off a bit early so we can kind of get on with it here. But we're going to go ahead and make an animated GIF. So let's let it go just a hair longer. Oh, you know, we're almost done. This is going to take maybe another 30 seconds, I think. Yep, 1880, almost there. Should take another 5 or 6 seconds to finish. Yep, there we go. So we're all done running the model. Let's go ahead and make an animated GIF now. So I'm going to type make GIF. And it's going to take all those SVG files from the output directory, convert them into an animated GIF, usually skipping the intermediate step in this particular case. So let's go ahead and let that finish up. Okay, so let's take a look at that GIF. So here we can see that we had a big distribution of cells ranging from blue, which is not very proliferative, to yellow, very proliferative. This is just like our introductory talk, but a 2D version. And you can see how the yellow cells are now have a much higher value than the blue cells. So they are really out proliferating the blue cells. And then as this tumor gets bigger, oxygen gets depleted in the center, and we get the necrotic core just to the very end of the simulation. So that's nice. So there's an example, right, of starting with a sample project, populating it, running it, taking a look at the visualization that's built into PhysiCell as a simple output of SVG files. And then once we're done, cleaning up our mess and resetting to a blank slate, and then repopulating and compiling a different built-in project. And so that's very nice. One last note on the configuration files. We are continuously migrating PhysiCell to put more and more model specification into markup files and configuration files in the config directory. And as we get better and better, we're going to put more of that specification and design into graphical tools, as we're going to see in session 2, the next session. And so just like with the source files, you may not need to touch these configuration files too much anymore, but it's still good to understand the structure of where you can find things. In particular, look in the config directory to find your setup files. And a lot of it is written as a markup language, so have an understanding of how markup languages are structured. They have an element, a beginning tag that's typically the name of your variable, some optional attributes that set properties of that variable, and then the actual value of the variable in between the tags, and then an end tag that matches the beginning tag. So know where you need to edit if you need to. And again, system developers may need to understand this technical structure a little bit better. Lastly, I want to point out that we now have support for saving and loading user projects. And so if you type make save proj equals and some unique name, you can save all the custom files that are specific to your project into one place in the user projects directory. So let's go ahead and take a look at that. So let's suppose now that we had made some changes to this project and we want to save it as our own project. So I can type make save proj equals, and let's just call it mine. It's going to save that project as mine. So if I go into user projects now, you may see that there's a new directory there called mine. And if you look here, you're going to have a few things saved: your make file, your main.cpp, everything in config, and everything in custom modules, the things that we expect to be specifically ours. So let's go ahead and take a look now. The other nice thing is you can type make list user projects to get a list of all current user projects. Right now, there's only one, the one that we just made. And now let's suppose we could do make reset. So we're back to a clean slate, but now let's suppose we want to go back and resume editing that project we were just working on. You could type make load proj equals the name of the project, in this case mine, and it'll load all those files up and we're ready to go. Just type make and compile and you're ready to go and building this project. So one last thing here is you may want to share this project with other people, which is kind of the goal of modeling and doing science, right? We don't just do it for our own fun, although we're having fun. We also want to share it with other scientists. And so one thing you can do is you can go into this user projects directory and you can zip all these files into a single zip file. Now, I've got to tell you, I think this is so important that in future release of PhysiCell, and probably by the time you arrive at the workshop, we're going to build in a make file called make pack as a rule to help you to do this. But for now, the command is cd./user projects, 2 ampersands. This will basically say that the next command will stay where it is, zip-r for recursive, and then the name of your project. In this case, it is going to be mine.zip. I'm going to kind of name the zip file the same, and then the name of the project, mine. And that'll zip everything that was in that project file. So if I go into user projects now, oops, let's see here. Now you see that this mine.zip is here. This would be the file that you would want to email or send to a collaborator, and you would tell them that they ought to unzip that file in their user project directory, and then they would be able to create and run your project just like you. And in the future, I think a great future project for PhysiCell is going to be a way to start kind of formalizing projects. Do we create maybe a custom XML object that lists all these custom files, the name of the executables and provenance, like who created the project and the version of it, things like this that we can kind of bundle and help us with reproducibility and make it easier to compile and share these things with other people. So that's a future project that's ready for anyone who wants to take it on. So thank you very much for joining me for session 1. And next session will be learning about how to use PhysiCell Studio, how to make some of this stuff even easier to access and do. So we'll see you around.